Good afternoon. Time for another lesson that we have here on video. Today we are in Unit 5 and we'll have this video about Lesson 5, some information that's happening. This is a great hands-on lesson that we'll kind of do under video, so getting you caught up, and feel free to watch this a second time if it was too fast in class or this might be your first time through. Starting with our warm-up. Lesson 5.1 starts with this Ferris wheel picture, and so Claire's elevation on this Ferris wheel at different times, t, gives us the different height that she is off the ground. So if we picture where she is off the ground here, as she goes around, we can tell that here she's going to be a little bit off the ground, part way off the ground, and then here she's going to be at her very highest point, and then as the Ferris wheel keeps turning, she'll come back around. So if we look at right now, at a time of 0 seconds, she's at the top of the ride. So here, she's at her highest point at 0 seconds. Assuming the Ferris wheel moves at a constant speed for the next 80 seconds, we can complete this table because we can see how high she was for the first 80 seconds to get to this high point. And then after she's at this high point, let's say she's gone around this way maybe, and now that she's at this high point here, 212 feet, she's going to start being again at lower and lower and lower points until she's right back where she started at another 80 seconds. So she's going to eventually end up back at 0. And so her height at 20 seconds from now is actually going to be right at the same height that she was 20 seconds before right now. See how I can go either way? And those two are both at the same height. So her height 20 seconds from now is going to be the same as where she was 20 seconds ago at 181 feet. And we can say the same thing when she's here at about 40 feet, or 40 seconds. Her height 40 seconds from the top is going to match because this Ferris wheel is moving at a constant speed. And so what we're seeing with this Ferris wheel is that right here at the cutoff point, to go along with what we thought of in Lesson 4, we have a reflection going on here. The same numbers that we see coming out from this reflection point are the same as what we see after the reflection point. So just like the graphs we were looking at, as far as reflecting, this one we could say it's reflecting over that y-axis, because right here is where it's gonna split. So if here at our halfway point, in fact it's going to match one of the graphs we'll see shortly, at 0 times she's at her highest point up here, and then at 80 seconds ago and 80 seconds from now is when she'll be down at the lowest point, and then she'll come back up. We have a graph that's going to look like this. And however many times that Ferris wheel goes around in a circle is how many times she will go up and down and up and down and up and down. So this kind of looks a lot like reflection when we can reflect something across the y-axis. But I see that our lesson 5 is talking more about symmetry. And you may remember from your Unit 5 check for readiness that there's two kinds of symmetry that we're interested in. There's reflective symmetry, and there's rotational. And this reflective and rotational symmetry, we actually also have another name for them here in Algebra 2, and in other classes, of course. We call those even and odd functions. And one way that I tend to remember this is that reflective with that E are even functions. So I'm going to build off that E and remind myself that reflective is an even function. And those that have rotational symmetry, we would call odd. So reflective even and rotational odd. Now this card sort, you had a chance to do it in class. You already might have some sketches drawn there for different graphs, and you can feel free to go on to the next section, fast forward a little bit. But I'm going to show a series of graphs that we have, a set of cards, and we're going to try to sort it into the reflective column or the rotational symmetry column. And we'll have a couple key points that we need to remember along the way. So our first graph, card A, looks like this. I think we have seen something kind of like that before, and if we really think about it, we could fold it right in half, or we could reflect it completely all the way over by flipping it completely over the y-axis, and we would have reflective symmetry. So this is one that if I were to hold up a mirror right here in the middle, I would see the same graph over and over. In fact, that's why they call it reflective symmetry. Now I'm grabbing my mirror out of my across from my classroom here, so we can actually see that happen. When I put my mirror right up on that axis, you can see that I get the same shape all the way across. So it's reflective symmetry because I can take this mirror and reflect that same exact graph and have it match up completely. So let's sketch what that first graph looks like. That is an even function that shows reflective symmetry over the y-axis. This is where all of our x's become negative x's and negative x's become positive. Our second graph looks like this. Now this one's not reflective because I see here from the origin going to the left, it dips down first. And from the origin going to the right, it goes up. So if I were to put my mirror here in the middle, right on the axis line, you can see what it would look like if it was reflective symmetry. This graph looks very different. So we can think of it that way as well, thinking about what that mirror looks like. This one, though, has rotational symmetry. So if I were to spin this graph with my pen right on the origin here, and were to spin that graph 180 degrees, it is exactly the same with rotational symmetry. Now, a lot of you on your unit check for readiness looked at this and you had maybe forgotten about rotational symmetry, but as soon as we mentioned it in class as a possibility, you were like, yes, I remember that. There's some clear plastic sheets somewhere in the room, and those might be helpful in coming lessons. If you ever need to trace something like this to see if it has rotational symmetry, just make sure you're using one of our whiteboard markers. You can trace it right on top of your graph like that. Put your pen right in the middle and spin the top clear piece of paper, there's your top piece only, to see if it matches up. And in this case, it's a perfect match. So this one has rotational symmetry. Let's sketch this here with our rotational. It's an odd graph that we have. And I want to make it really clear that these little bumps in the middle are larger than the outside bumps like this. So it starts going down, ends going up. I need a big bump that's going to end up going up like that. So this is rotational symmetry. We would call that an odd function. So we've mentioned some key points so far. This reflective is always across the y-axis. And this rotational is always 180 degrees around the origin. So we're going to find that odd functions have to go through the origin for them to be rotational 180 degree symmetry. And reflective can be whatever they're looking like, but it always has to be reflective across the y-axis, not across the x-axis, top and bottom. We're going to go through our next couple graphs a little bit faster here. So let's see what we have. Here's graph C. we can see that this thing, it's not reflecting the same thing side to side, but it is rotating around. So if I were to trace that and rotate it all the way around, it would be the same looking graph, right side up, and rotated all the way around. So let's sketch this one in our rotational column, going through the origin and spinning back and heading back down. Graph D. Well, if I spin this one around, it's going to look very different. This looks almost like a letter W. If I try to spin this 180 degrees, it's more like a letter M. So that's not going to work out very well. What we see instead is that this is reflective symmetry. I can fold it in half and see that the two parts are going to line up exactly on top of each other. So a little reflective symmetry here. This one's got some waves going to it. And waves can sometimes be rotational and sometimes be reflective. It actually kind of reminds me a lot of this one that we just saw. This one had that high point that didn't go through the origin and happened to be perfectly balanced on both sides. This one does go right through the origin. And so if I were to trace this one and spin it, we would see some rotational symmetry happening here. So again, I'm going to trace it, put my pen right in the middle, leave the bottom paper right where it is, spin this graph around, and it lands right on top. Let's sketch this graph for rotational symmetry. It's got to go right through the origin. A little reflective symmetry going on here. This one does go right through the origin, but we still can't spin it and have it be the same exact graph. The way it is here, it's a W shape, and if I were to rotate this, even though it goes through the origin, it changes the shape of the graph. It's now an M, so we're not winding up as the exact same graph. So we only have reflective symmetry. In fact, you can't have something that is both even and odd at the same time. They cannot do that. Horizontal line happening here. You're not missing the graph. That's all it does is go horizontal. That looks pretty reflective to me. And last but not least, a little zigzag happening, going right through the origin. From the origin, they go opposite directions. A little rotational symmetry happening here. Zigzag. Now the second part of this sort in section 5.3 actually asks you to match up some coordinate cards like this with the graphs that they match up with. So we could certainly look at each of these points and find something that it's going to match with. In fact, this one, I know what kind of graph I'm looking for. And so I think I've got it here. Maybe. I know I'm looking for something that's a perfect mirror image, and so at first I thought it was this one, but I have zeros at 4 and -4, and here these zeros are at 3 and -3. So I don't quite have a match there. Let's see if I can find the match. Of course I don't have any. I don't have every single coordinate on here. Oh, duh. Oh no. I was looking for zeros at 3. Anyway, look at that one. There's the 3s all the way across. I know that that's our horizontal guy happening right here. So it doesn't matter if our x's are positive or negative, our y's are a perfect match there. -1, it's up at 4. That can't be this graph. Huh. That This guy? Yeah. All right. So we can match up some coordinates and start seeing some patterns that are happening. Even that one's not there. -4. There we go. This guy is a match here for this one. So some things I notice here. I'm looking at an odd function that we have, and I'm noticing that at -4, our y is positive. And when I flip the sign of the x to be a +4, the y also flipped its sign from negative to positive, or positive to negative. So looking at the coordinates of what's going on here, knowing that this was an odd function and had rotational symmetry, when I change the inputs here, the odd, or the input values had to change their sign, and the output values had to change their sign as well. So we really start seeing some differences going on here. When one changes, the other one also changes. That's going to be true for every single odd function that we have. So if you'll go with me onto your 5.3, when we have coordinate pairs of odd functions, something that happens, one of the things that we can talk about is that when the input changes sign, the output does too. Every single one of our odd graphs that we have, when we look for its coordinating point in the new graph, when we have it kind of rotated around, every point that we're seeing, let's say this exact point here at 1, +4, has a coordinating point in the opposite quadrant. So our x turned negative and our y turned negative. We reflected this graph across both the y-axis and the x-axis. We had to flip and flip again, because just flipping it once would put us here in quadrant 2. Flipping it again puts us down into quadrant 3. The same is going to be true with every single one of our points that we have. Anything that's, say, here in quadrant 4, +x, -y, when we rotate it, goes to a +x and a -x and a +y. Oh, too many things that we're flipping here. So it goes to that opposite, and that's going to be true every time with our odd functions. Because we have to rotate all the way 180, everything is changing its sign. Now that's very different than something when we're looking at an even function. So here's one of our even functions, in fact one of the first ones we looked at, and it matches up with this set of coordinates. So -2, +3 matches up with +2, +3. -4, 0 matches up with +4, 0. So for here, each of our points that we have, when we use the same value, x, in a positive and switch it to a negative, doesn't matter, the y's are going to stay exactly the same. When we change from a -6 to a +6, no change in the y value. And we'll see that for every kind of even graph that we have. So something we notice about those coordinates, when the input changed sign, there is no change to the output. So we're talking about odds and even functions, right? So if you want to make a little table of values, ooh, you can't see that. If you want to make a little table of values, we could see that what it looks like for our original and where we would see for an odd, but that's kind of a nice way to think about it. If we have a negative 6, 1, we'll have to have a point at 6, 1. If we have a negative 2, negative 3, we'll have to have a positive 2, negative 3. So when our input changes sign, our output stays the same for an even function. Looking at those same kinds of points with our output, if we change the input sign from negative 6 to positive 6, we also change the output sign as well. Negative 2, negative 3 would become positive 2, positive 3. So our table of values would look something like that. And when we graph it, we could look at whether it was reflective across the y-axis or rotational about the origin. There is always another option too. We have even graphs, we have odd graphs, and we also have things that are neither even nor odd. So I just want to remind you that there is a possibility that something might not be either odd nor even. So a neither graph might be something like if it, let's see, could it be, how would we have one? Something that doesn't really even start to have a consistent pattern like that. We might see a neither graph going on like that. I can't rotate this. I can't reflect it. It's not going to be the same. And even if we take one of our reflective graphs, something that was reflective, like I'm going to think about this one here. If I take that graph and I move it to the left or to the right, since we're in the chapter where we're talking about moving things, if I move that simple parabola off to the side here, all of a sudden something that was reflective, like this, is not reflective here, because if I reflect that over the y-axis, all of a sudden I've got the whole, like the vertex is going to be a negative value. That's going to be in a whole different place. So this would also be a neither. And the same thing is true if we have something like this, but we take it off of the origin. I can take the exact same shape of a graph, that zigzag shape, and by moving it up off of the origin, it's still rotational if I can put my pen here, but by the definition of something being an odd function, I have to only ever do it at the origin. So I just want you to know that before you tackle the practice problems here for Lesson 5. With those in mind, feel free to go ahead and review the lesson summary and tackle some practice problems. It's just going to ask you to do some classifying, maybe filling in some tables of values if we know some even functions. Think about what those are going to look like. Enjoy. Bye, friends.